We keep exploring. We're talking about vectors, and we're in the part of the course where our focus is geometry. And geometry is really important because we're going to be speaking about multivariable, so we're in a higher dimensional setting. So we have to be comfortable working with points and also with vectors in higher dimensions. So we're going to keep talking about vectors. Now, why do we care so much about vectors? Well, one of the reasons we care about vectors is we're thinking about the vector as representing a difference. And if you think about calculus, we talk about the derivative. You think about, well, it's how y is changing with respect to x, or what's the change in y over the change in x. That's differences. So vectors are very important to understand. And they're going to be very important for our course, so it's good to get a good handle on them. Now, last time we introduced vectors, we said, hey, we can add vectors, we can scale vectors, we can even subtract vectors, but can we multiply vectors? We didn't get to that. So we're going to look at that in the next few lectures. Well, okay. Obvious thing to do is entry-wise, because that's how you add. If I want to add two vectors, add the entries. If I want to scale a vector, scale the entries. So it seems reasonable to say, if I want to multiply vectors, I should multiply the entries. And that's a very reasonable thing. In fact, there's a lot of pros about this. It's easy to do. It's easy to remember. It's intuitive. And I can't help but notice that there's even more space underneath it. Probably things like, it likes long walks on the beach. It does your dishes. No. So there are cons. It turns out that even though it's easy to do, it's useless. That's a bold statement. Now, let me explain what we mean. There's no geometry inside this type of product of vectors. So when we talk about geometry, we're talking about the geometry of space. Now, there's a tendency for you young people who were born in the last 1,000 years to think about geometry, oh, that's like I have points in space and there's coordinates, and so that's how I should operate. But actually, the idea of coordinates is relatively modern. You can do geometry with never referring to coordinates at all. So anything which is coordinate sensitive, in other words, depends on how you pick your coordinate system, is not working geometrically. And so we don't want to do that. So okay, so I claim that this type of product is coordinate sensitive. So by changing your coordinate system, you change the output. Now, as an example, suppose I take these two vectors here. Now, they're pretty tame, and what you might see, it's a little bit faded, but you might see that there's a set of axes. So you can imagine, I'll highlight these axes here first, that I set my coordinates up so that my vectors lie along the axes. So I can talk about what's happening when I change. Well, for instance, what I see is that the vector here, the change, well, it looks like something of the form A0, because all my changes in the first direction, no change in the second. This vector is sort of the opposite, 0B. So if I were to do entry-wise multiplication, what would I get? 0, 0. I'd get 0 out. The 0 vector, which is a very interesting and some people might say directionless vector. All right, but that's one set of coordinate systems. Suppose now I tilt my coordinate system. And you might say, are you allowed to change your coordinate system? The answer is yeah. Oftentimes, physics comes down to saying, choose a good coordinate system, and the problem becomes easier to do. We're going to see this a little bit in the second part of the course. So now, if I look at points, well, what do I see? Well, this vector changes in both directions simultaneously. So I'll say it's something like C comma D. And this one, again, it's changing in both directions, at the same time, E and F, and all these numbers are not 0. So when I multiply them together, I get C times E and D times F, but none of these numbers are 0, so this is not the 0 vector. So now what you see here is that the output, in other words, this product, it depends on your coordinate system. So that's why this is not something which is inherently geometric. So it's something we can't use. All right. Well, all is not lost. There are products that do work, and we're going to talk about them. So today, we're going to talk about one of two. It's called the dot product, and its name comes from the symbol. You'll notice it's a dot. So if you see a dot, that's the dot product. Now, how does it work? And the answer is, it actually is very similar to what we just did, with one small difference. So the idea, we said, might be a really intuitive one. It's just to multiply the entries together and says, hey, that's beautiful. Do that. Multiply the entries together. But don't use those numbers to make a new vector. Instead, add them all up. And if you do that, the result is a number. Now, sometimes I'll say a number is referred to as a scalar. So when I say number slash scalar, that's just saying sometimes people call it a number, some people call it a scalar. But the point is, I start with a vector, I dot it with a vector, and the output is a number. So if I take ABC and I dot it with DEF, I get AD plus BE plus CF. Again, you'll notice it's the same thing we did before, but we're adding things up. Nothing special about dimension 3. So if I do it in 2 dimensions, AB dot DE, well, multiply the first entries, AD, multiply the second, BE, add them up. Okay. Well, let's try this out. Let's compute some dot products. So I don't have any vectors written down here, so we'll have to make some up. Okay, so should we start 2D or 3D? 3D? All right, going all the way. So I need a vector.
2.
Well, normally if it's a 3D vector, you'll need more than just 2. Okay. 2 again, and someone said 0. Okay, dot. Now we'll need a second vector. 13 and 8, and I think someone said 5. Maybe, I don't know. I'll write it down. Okay. Don't worry, we'll have space. We'll do more. So, what do you get? Well, multiply the entries. 2 times 13, 26. 2 times 8, 16. 0 times 5, 0. 26 plus 16 plus 0, 42, which is the answer. Some might say the answer to life, universe, everything. But in this case, it's the answer to that dot product. All right. Good. Well, we have space. We can do at least one more. Should we do another one? 3D or 2D or 4D? 4. Oh, the fourth dimension. Okay. We can do it. All right. So, if I'm doing a 4D, how many entries am I going to need in my vector? 4. Okay, yeah, you've cracked the code. Okay, so I need 4 numbers. 5?
Pi.
Oh, pi? Pi. I thought you were like making up one of these phone numbers that you see on movies. 5 pi. Did I misspell it? Well, this isn't Thanksgiving. We can only have so much pi. We'll throw some numbers in.
E to the I pi.
Okay, -1. All right. I know the answer to that one. Okay. Dot. Now, let's throw some other things in here. T squared, e to the t, tau. Okay. Not what I was expecting, but the point here is that these are anything we want. These entries in these vectors can be anything we want. And as we go on through the semester, we want to be able to get to the point where we're comfortable with functions in these vectors. And when I say later in the semester, like next week, you know, so we're not that far off. Okay, so what would this be? 5t plus pi t squared plus, ooh, you're being fancy. Okay, so it's e times e to the t, and you can combine them because they both have e. So it's like e to the t plus 1. Yes, that's true. And then minus tau. Okay, all right. So we can do these things. Now, let's talk about this product. What are some things that are true? Well, I think it's pretty easy to say, look, it's not hard to do this product. We didn't have much struggle doing these dot products, and it's not hard to remember, but there's something even more important. It's useful. In other words, there's some geometry involved. It's not a coordinate-sensitive number. Not at all obvious when we talk about it, given that it's like, oh, just multiply the entries, add them up. But we're going to get to that. And we're going to get into that in a few moments. But first off, some various properties. So the first one, u dot v is v dot u. In other words, it doesn't matter what order you take the dot product, you're always going to get the same number out. Now, why is that true? Well, you just think about it, because what's happening is you're multiplying entry-wise. And when you're multiplying entry-wise, and before you add, multiplication doesn't matter. 2 times 4 is the same as 4 times 2. I can pull out factors. So, for example, if I have a scalar, or a number, times the vector u, and I dot it with v, I can just pull that scalar out. So that's the scalar times u dot v. I can distribute. U dotted with v plus w is u dot v plus u dot w. And so it's sort of intuitive. Now, how do you check these properties? And we'll go through and actually verify one. But the thing is, you just check it and you verify what happens entry-wise, and you'll see that things happen. 0 dot u is 0. Does that make sense why that should be true? Yeah, it should make sense, because 0, the 0 vector, is the vector where all those entries are 0. So when I do that multiplication, I have a whole bunch of zeros adding up, and so I should get 0 out. Now the last one, and here's when we start saying, aha, there's a hint of geometry. If I take a vector and I dot it with itself, I'll get the magnitude of the vector squared. So let's verify that one. So how do we verify something? We just say, well, let's just write the vector. And we're going to work in 3 dimensions. It doesn't really matter which dimension we work in, it's the same proof. But we'll do it in 3. So I have my vector. I'm going to say it's A, B, C. So there's my vector. So let's look at u dot u. So A, B, C dot A, B, C. Because that's what u is. U is ABC, so I have ABC dot ABC. All right. Well, according to the rule, what do we have? Yeah, A squared, because A times A, and then B squared, and we're going to add, and then C squared. Good. Now, you might notice A squared plus B squared plus C squared can be written, it's kind of a weird way to do it, but it can, the square root of A squared plus B squared plus C squared, quantity squared. Now, why do I write it that way? Well, have we seen the square root of A squared plus B squared plus C squared before? Yeah, it's related to the distance formula, and in particular, it's the distance from the start of the vector and the end of the vector, which means it's the length, or the magnitude. So, this is the magnitude of the vector squared, which is what we wanted to show. Now, you might say, that seems pretty weak to say it's useful geometrically because it's not very hard to get the magnitude. Okay, here we go. This is a good one. Now, all that fun stuff you learned in trigonometry, and you're like, I'll never see it again. Well, this one really is one of those ones you probably may have forgotten. The law of cosines. You don't have to memorize the law of cosines. But you do have to believe me that this is the law of cosines. You can go check it, call up your old trigonometry teacher and just say, I want to verify. My instructor said this was the law of cosines. He wasn't lying, right? It is true. That's what you get. Now, what is the law of cosines? One way you can think about it is the law of cosines is almost like a generalization of Pythagorean theorem. And why do I say that? Well, the idea here is if I have a triangle where A, B, and C are the side lengths, and theta is the angle between the sides with length A and B, that C squared is A squared plus B squared minus 2AB cosine theta. Suppose for a second theta were pi halves, or 90 degrees. What is the cosine of pi halves? It's 0, which would say that C squared is A squared plus B squared. That's the Pythagorean theorem. So this really is sort of a nice generalization. It says, look, you don't have to have a right angle in the corner. This is true. This is how you adjust. All right. So my claim is this picture is going to help us give a nice geometrical fact about the dot product. Well, not quite that picture. What's missing? What haven't we drawn? There's no vectors. I'm claiming something about vectors. Well, that's easy to fix. Put vectors in. So I'm going to have the side that was length A, I'm going to call that vector U. The side that was length B is going to become V. And you'll notice that I didn't just draw them randomly, but I made it so that their starts, or if you call them their tails, that their tails are together. So I have U and V coming out from the same point. And now this third side, well, what is that? Well, I can also represent it by a vector. And what's the right vector? The claim is that it's U minus V. So how can you check? Well, one way to check is if I go V, and then I go whatever this vector is, so those two together, the same is just going U. So V plus whatever this is has to be U, so this has to be U minus V. Okay, so that's not so hard. Now, here's what we're going to do. We're going to find the length of U minus V squared. Okay. All right. So far, so good. And we're going to find this length in two different ways. Now, what two ways can we use to find that length? Do you see the two ways we can do it? We can use the law of cosines. Or, is there anything that lets us compute a length squared? Maybe something related to a dot product type thing.
The distance formula?
Perhaps I'm being too subtle here. Is there anything that lets us compute the magnitude squared of a vector? Oh yeah, if I take a dot product with itself. So I'm going to do it in two different ways. And here's the fun thing. If I compute something in two different ways, what has to be true about the answers? They have to be the same. They may not look the same, but they have to be the same. It's the subtleties of their difference of their expression which gives us insight. That's why it's nice to be able to do things in multiple ways. Well, let's see. I think we'll start with the dot product. Okay. So the magnitude of the vector squared is the dot product of the vector with itself. So it's U minus V dot U minus V. Now suppose you just saw this and you'd forgotten about the rest of the talk, you maybe didn't know that these arrows meant vectors, and you said, oh, I have u minus v and a u minus v multiplying together, what would you do? You'd distribute, you'd FOIL, you'd expand. Well, you're allowed to distribute. That's what this is telling us. So we distribute. And if you distribute, you get u dot u, which is like your u squared. You got your v dot v on the end. That's like your v squared. And then you got your 2uv, and that's 2u dot v. Okay. It's the same expansion that you'd see in normal algebra. Let's talk about a few of these terms. Is there anything we can do with u dot u? Yeah, it's the magnitude of u squared. What about v dot v? The magnitude of v squared. And what about minus 2 of u dot v? Well, the answer is it's still minus 2 of u dot v. All right. So far, so good. Now, that was method number 1. Law of cosines will be method number 2. So I'm going to think of this in terms of law of cosines. So I'm going to think of these as being the magnitudes of these sides. So this is my C, here's my A, here's my B. And once I apply the law of cosines, I get that C squared, that's the magnitude of u minus v, quantity squared, is A squared plus B squared minus 2AB cosine theta. All right? And now the magic. Compare. Those match, and we already said they had to be equal, so what else has to match? Well,
It has to be 1.
well, it's not that cosine has to be 1, but it's that u dot v has to u times v cosine theta. There we go. U dot v is the magnitude of u, the magnitude of v, cosine of theta. What is theta? Theta is that angle when your tails are together. Now, what's nice about this? Notice that the magnitude of u, that's something geometrical. It's the length. It doesn't depend on your coordinate system, because I can think about length as just as a vector. It's like I'm measuring the arrow. Same with magnitude of v. Again, that's the length. That's geometrical. And cosine theta, theta is geometrical. It's the angle between the vectors. The angle's not going to depend on what coordinate systems I put in. So this tells me that the dot product has a geometric meaning, which means it's awesome. Okay, good times. Now, let's try this. Here we go. So there's another way to write this, by the way. So if you solve for cosine theta, because you can, you get that cosine theta is u dot v over the magnitude of u, magnitude of v. And one of the things that this tells us is that we can use dot products in the following way. If you want to find an angle between two vectors, more particularly if you want to find the cosine of the angle between the two vectors. Now this might come up, and I will tell you, if you ever see a problem that says the word angle, 95% of the time, there's probably lurking in the background this formula. So it's good to know that formula. You might be wondering, has such a problem ever appeared on an exam? Yes, it has. No, that's not what you're wondering. Will such a problem appear on the next exam? I don't know. Hasn't been written yet. But be prepared. So, I said it's geometrical, so let's do something geometrical. Here we go. I have a vector u, I have a vector v. Here, there's an angle of 3 pi fourths. And I'm actually told how long u is. Magnitude of u is 3. I'm told that the magnitude of v is 2. Sorry, root 2. And I want to find u dot v. All right, so let's do that. Probably should be straightforward. U dot v, according to this, magnitude of u, magnitude of v, cosine theta. Well, what's the magnitude of u? 3. How do we know that? Yeah, they told us. It's like they want us to know things. What's the magnitude of v? Root 2. By the way, this dot here is not a dot product, it's multiplication. Okay. Cosine theta. What's theta? Oh, let's be careful here. What is theta? Now, sometimes we like to make you say, oh, it's this because I see it clearly marked. That's an angle. Is that the right angle? Why is it not the right angle? Yeah. See, notice how the vectors are drawn. See, the tail for u is way over there. The tail for v is over here. So the tails aren't together. So 3 pi fourths is an angle, but it's not the right angle. Now, how do you find the right angle? Well, the way we find the right angle is, remember that vectors, they can be moved. So we're going to move our vector so the tails are together. I think in this case it's easiest to move v. So I'm just going to move v across. So now this is v. And when I say this is v, I mean this is v. This is not like a copy of v, because v is not dependent on location. I can move v wherever I want. So if it was 3 pi fourths over here, what's the angle over there? It's pi fourths. Okay, so what angle goes here? Pi fourths. Good. Do you know what pi fourths is, by the way? Or rather, should I say cosine of pi fourths? Root 2 over 2. Root 2 over 2 times root 2 becomes... Well, the root 2 times the root 2 will become 2. So you have 2 halves, or a whole, also known as 1. Okay, so that's 1. So what's our answer? 3. Okay, good. Now the next one. Find cosine theta, where theta is the angle between some vectors. Well, we didn't write the vectors down. This means audience participation. Okay, all right. So give me a vector. Let's just do numbers now. No crazy Greek letters. Pi.
9.
9.
-4.
-4. Good. We're allowed negative numbers. Absolutely. That's one vector. Another one? -42. No, I don't think so. What? 7. There was something teen. What? 13. Ah, 13. Okay, and what? 11? 11. Okay. Now, on a test, we probably... okay, I'll give you some insight into the test writer's mind. Generally speaking, we tend to avoid unpleasant numbers because we don't give you calculators, and we're not testing you too much on arithmetic, just the right amount, just enough. So most of the time when we give you a number, it'll be something reasonable to work with. If you have something which looks incredibly unreasonable, we are desperately trying to signal to you, don't do what we think you're asking us to do. It's like, avoid this. Use the power of your minds to do it some other way. So be suspicious when you see weird numbers. Okay, so cosine theta. Now notice we're looking for cosine. That's cool. All right. So what do I need to compute? Dot products and magnitudes. Okay, so we're going to look at u dot v over magnitude of u, magnitude of v. So whichever one you call u and whichever one you call v, it doesn't matter because it's symmetrical. So we'll call the first one u. Okay, u dot v, entry-wise multiplication. And you asked for it. You got some fun numbers. Pi times 7. 7 pi. 9 times 13. 117. Good. Minus 4 times 11? Negative 44. Okay, downstairs. When you see a magnitude, square root. Okay, magnitude of u. Well, square root of, what do you do? Yeah, you square and you add them up. Okay, so pi squared, and then 9 squared is 81, and negative 4 squared, or is it negative 16? No, you're right, it's 16. Just checking, keeping us honest. All right, next one, 7 squared. 49. 13 squared. 169, good. 11 squared. 121. Now, what do we do at this point? The answer is, we're done. It said find cosine theta. That's cosine theta. Now, if it says simplify, then we're like, ugh. And we spend a lot of work simplifying it. But if it just says find it, then we can find it, we can stop. Now, sometimes I will stop, and now I'll stop because it's just sort of, there's not really much insight gained from simplifying. Occasionally, there's insight, and that's when I keep going. But okay. Now, suppose I see these two vectors, u and v, and you'll notice that I put a little tiny square-looking thing here. What's true about u dot v?
Zero.
It'd be 0. Why is it 0?
Cosine theta.
Yeah, because remember, there's a cosine theta. If it's a right angle, cosine of a right angle is 0. So regardless of the size of u or the size of v, that 0 really makes it tough. It's got to be 0. So we have this nice fact. We say that two vectors are orthogonal, another word is perpendicular, when their dot product is 0. So dot products are really useful for saying, are these two things perpendicular? Or maybe we already know the two things are perpendicular, and we can say, okay, what information does that give us? So we're going to use this more often than you might think. So whenever I think two things might be perpendicular, or I know they're perpendicular, I say, aha, dot product is 0. Let's see where that takes us. Let's do an example. Again, small example. Find all values a so that a comma something something and something a squared comma something are perpendicular. Okay, for the benefit of your instructor sanity, single digit numbers. Okay, so 3, 5, 1, and there was a 7. Okay, so I have some vectors, and I want to ask, when are they perpendicular? And now I'm really nervous that maybe they're never perpendicular, so I'm going to make this a -5. Okay, good. Now I know that they're going to be perpendicular at some point. All right, guaranteed. Okay, so what do we do? They're perpendicular. What needs to be true? Dot product equals 0. So whenever you see the word perpendicular, one of the things you should remember, hey, if perpendicular is showing up and there's vectors involved, something where I have the dot product, I better get 0. Okay, so 0 has to equal a3 -5 dot, and that's an a, it kind of looks like a 0, 1a squared 7. So let's take their dot product. What do you get? A 3a squared minus 35. Now, normally we write this in powers largest to smallest. 3a squared plus a minus 35. How do I find when this equals 0? Well, is there a formula one might use for a quadratic?
Perhaps a quadratic formula?
Yes, perhaps a quadratic formula would be very helpful in such a setting. Okay, so we could say, what are they? Well, the solutions are you take, you come in front of the A. Now, of course, I regret choice of A, because usually we have A, B, and C, but okay. So it'd be, I'm going to put quotes around air quotes here. Okay, so negative what's in front of here, so negative 1, plus or minus the square root of 1 minus 4 times 3 times 35 all over 6. 2 times what's in front of the A squared.
Should it be negative 35?
Ah, you're right. Minus, minus, plus. Good. And what do we do next? We circle it, because I'm not going to go any further. Okay. 4 times 3 is 12. 12 times 35 is a big number. It's 420. And then you have 421, because you have to add the 1. And the square root of 421 is unfortunately not a nice number. So we'll just stop there. Okay. But the point is we can do these things. And normally when we ask you to do these things, we've planned ahead. We don't just randomly ask. All right. Well, how do we use dot products? These are all fun. But let's see how we can use it. So there's this nice idea called projection. What is projection? So here's how I think of it. I have a vector, and let me label these vectors. There's sort of an index here on the side, but I'll label them here so you can see it. I have a vector u. That's my vector u. And I have another vector v down here. And that's the long one. And what I want to ask is how much of u is going parallel to v? In other words, what's going with v and what's not going with v? So one way to think about it is to think that there's like a light above, and that u is casting a shadow down onto v. So there's this shadow here. And the resulting vector, this part right here, that vector is what we call the projection. Whoops, I can spell projection. Okay, it's this one. It's the projection of u onto v. So this is onto v. So I'm going, v is the one I'm projecting onto. So the result is going to be a multiple of v. Now I want to be careful. Sometimes I like to use the terminology, how much of u points in the direction of v. But when I say the word direction, I have to put quotes, direction of v. Because it is possible that you could be in a situation where I have a vector v and I have a vector u. And here when I do a projection, what happens? It points sort of in the opposite direction of v. But in both cases, if I'm pointing in the same direction as v or in the opposite direction of v, I'm always a scalar multiple of v. So I'm always parallel. So the projection, and that's what it says here, of u onto v is how much of u is parallel to v. So it's like we're taking this vector u and we're going to break it into two parts. And one part is parallel and one part is not parallel at all. Sort of the opposite, which is perpendicular. And you can see that in these pictures here. Because if I think about it, if this is my u, here's my v, what happens is that there's two things. There's the projection. So the projection is this piece. The projection of u onto v. Well, that's a vector. It's a vector. Then I can say, hey, there's this other vector here. And notice that this other vector is perpendicular to v because it's right angle. And if I take the projection plus this other vector, I get u. So it's really, in some sense, I'm breaking u up. I'm saying, okay, some of u goes with V, some of u goes perpendicular to V, how much? Okay, so that's the goal. So I want to figure out what the formula is for the projection, which means I want to find a vector. If I want to find a vector, what two pieces of information do I need? Direction and magnitude. Every vector has two things, a direction and a magnitude. So if I know those two things, I know the vector. So let's talk about the direction. Well, what can we say about the direction? Again, just think about intuitively, what should we have? What is the direction of the projection? If I'm projecting onto V, what's the direction? Parallel to V. So the direction is the direction of V. Now, notice I put quotes here. We'll fix the quotes in a second. When we talk about the direction of a vector, it's a unit vector that points in the direction that we want. So that's why there's a 1 over the magnitude of V. Make it a unit vector. Unit vector is purely direction. Now, the fun part. What's the magnitude? Well, let's draw ourselves a picture. In fact, here we go. That was quick. There's an angle here. I'll call it theta. That's the angle between u and V. Now, V may or may not be the right length, but u certainly is the right length for this picture. So I'm going to focus on u. Here I have a nice triangle. So if I think about it in terms of theta, I have u, and I can think of the length of u as being the hypotenuse. I want to know the length of the adjacent side. What relates the adjacent side and the hypotenuse in a right triangle? Cosine. So I can say that cosine theta is going to be the length of the projection of u onto V divided by the length of u. So the magnitude of the projection, just move the u across, is the magnitude of u times cosine theta. And now we're in business. We're ready to go. Now you might notice again, I put quotes here. You might say, whoa, why do you keep quoting so much? What could happen with this value, magnitude of u cosine theta? Could be 0, that's okay. Could be negative, because cosine can take negative values and magnitude can't be negative. But now, here's the beautiful thing. When the direction is in the wrong way, the magnitude is the wrong sign. So the two quotes cancel each other out. Ah, two wrongs do make a right. Okay, so here we go. Combining magnitude and direction, whoop, here we go. Maybe try to make that so it reads well. We have that the projection of u onto V, we take the magnitude, which is the size of u times cosine theta, times the direction, 1 over the magnitude of V times V. Now, I'm just going to combine. Here are my constant terms in front. And looking at the numerator, I say, hey, it looks an awful lot like that dot product thing we just talked about. I'm just missing that magnitude of V. So I put it in. Easy enough to do. And then I say the top, that's a dot product. That's u dot V. And the bottom is a dot product. It's v dot V. So it's u dot V over v dot V times V. And that's it. That's the formula. Now, there's a temptation here. Let me point out the temptation to say, hey, I see why this works. Because this, if I just write it down, that's u dot V, v dot V, and then I multiply it by V. Well, yeah, just do cancellations. I've got a V here, and a V there, and a V there, and a V there. Ah, it's u, of course. It works out. Cancellation doesn't work this way. Let's just see some simple examples. For instance, 16 over 64, if you cancel the 6's, do you get 1/4? Wait, no, that doesn't work. Okay, all right, look. That's a fluke. All right, better yet, 19 over 95. Okay, cancel the 9's. Well, anyways, it doesn't work that way. Just Be careful, be careful. All right. But that's a formula. All right. Now, this last piece up here says we can do what we talked about before, which says if I wanted to, I can take any vector I want and split it into two parts. One part which is parallel to that second vector, and another part which is perpendicular. And we will be doing this pretty soon in the near future. And the way you do it is you find the projection and then take the difference. Okay, so let's do an example. So for two vectors, let's find the projection of u onto v, and the part of u which is perpendicular. And in case you don't know, sometimes we do shorthand. This symbol here, which looks like an upside down capital T, means perpendicular. So split it into two parts. Okay, so what are our vectors? Okay, tell me what you want for u. 1.
2.
2. 3. I kind of like where this is going. 4. 5. We'll throw in a negative just for fun. 6. Okay. So, here we go. If I want to find the projection of u onto v. So, u dot v over v dot v times v. So that's the formula. It's good to know the formula. Okay, what is u dot v? Well, we do it. So it's 1, 2, 3, dot 4, negative 5, 6. So we have 4 minus 10, negative 10, and 18. Divided by v dot v. 4 times 4, 16. Negative 5 times negative 5, positive 25. And then 6 times 6, 36. Times by 4, negative 5, 6. We can clean it up a little bit. Let's see, we have 22 minus 10 is 12 upstairs. Downstairs, we have 52, 77, I think. 4, negative 5, 6. Okay, so that's the projection. How do we find the perpendicular part? Well, let's take your vector, 1, 2, 3, and subtract. 12, 77, 4, negative 5, 6. So this is the perpendicular part. And that's it. On a side note, you might say, oh, this is easy. We'd probably never see this on a test. This problem here, other than the numbers, not even the perpendicular part, just the projection, that was a final exam problem a couple years ago. That was a dark, dark day for our department, that final exam. We don't speak about the fall 2011 final exam anymore, but anyways. Different story for a different time. Okay, so I have a little bit of time, 1 minute at least. So enough time to answer this question. Suppose I'm told that W is the projection of V onto U. What is the projection of W onto V? So W is the projection of V onto U. What is the projection of V onto W? Do we have enough information to figure this out? Now, sometimes it might be we don't know, we can't figure it out. Any thoughts? W. It is W. Why? Well, let's think about it. Which way is W pointing? It's parallel to V. Now, how do I know that? Because I'm projecting onto V. Whatever I project onto, I have to be parallel to that. So W is parallel to V. Now, W is parallel to V. I want to project onto V. How much of W is parallel to V? All of it. So when I project back onto V, what will I get? All of it back. And so that's why. And we're